So this video goes over two of the problems that were in the notes presentation. So this problem here deals with the ball moving in a vertical circle. This would be like if you were twirling a ball in front of your body. So we know that several forces act on the ball. We know that the weight force is acting down, and there's also a tension force acting towards the center of the circle. This may also be thought of as the centripetal force. The acceleration is also going to point into the middle of the circle. So in order to make analyzing this problem easier, we are going to say that pointing into the middle of the circle is the positive direction. So let's apply Newton's second law to the top. So we know that there's a weight force and a tension force both pointing into the middle of the circle, and so both forces are positive, and they can be set equal to the mass times the acceleration. And the acceleration here is equal to the centripetal acceleration, which is equal to velocity squared over the radius. Next, we can look at the ball when it's passing through the bottommost part of the circle. At this point, the tension force points into the circle and weight points in the exact opposite direction. So we know that the force is going to be equal to the tension minus the weight. And this is once again equal to the mass times the centripetal acceleration. Next, we may want to look in more general cases, which is equal to the tension plus mg sine theta equals mv squared over r. Now you're probably wondering why, in order to look at the component of the weight function pointing into the circle, right, because we're looking at all these objects and their components pointing into the circle, you're probably wondering why the weight function is equal to the sine theta and what this theta angle even is. So to explore this idea a little more, we are going to look at the ball when it is not quite in the left, right, bottom, or top of the circle. So right around here. That looks like around 2 o'clock if this were a clock. So we can make this portion of the weight force into a triangle where this bottom x component part is just like the horizontal radius of the circle. The theta angle is the angle between the positive x-axis and the position of the ball. We can tell that this other angle in this triangle is going to be equal to star, let's just say. So what we are going to be looking for here is the component of the weight force that points into the center of the circle. And the other component is going to be the weight force that is tangent to the circle. So these are the two components of the weight force. We know that the tangent line and the line that connects to the middle of the circle are going to be perpendicular, which means that a 90-degree angle minus our angle for star is going to equal theta. And using our trigonometric functions, we know that the tangent line is going to be equal to weight times the cosine of theta, and the weight going towards the center of the circle is going to equal the weight times the sine of theta, just like what we wrote in our general equation. So just to double check, we can apply this general equation to 0, 90, 100, and 270 degrees. So looking at the right, top, left, and bottom of the circle. So at the top, theta would be equal to 90, and sine of 90 equals 1. So we just have tension plus weight, which is what we said before. At the bottom, theta would equal 270, and sine of 270 equals negative 1, so we have tension minus weight, which is like what we said before. And for the right and for the left, we know that theta is going to equal 0 and 180 degrees. So when you plug these angles into sine, it simply just equals 0, which makes sense because the weight force points directly down and does not have a component pointing into the circle. Alrighty, so next we are going to cover the problem with the car traveling around a banked track. So we know that there's a normal force and a weight force acting on the car like this, and we can expand this drawing of the car a little bit more so we can further look at the different angles. So here we have the same triangle and the same normal force as before. If we make this into a square, we also know that the angle in the upper right-hand corner is also going to be equal to theta. And we can extend out our normal line and the line of the triangle and then break up the normal force into its x and y components as shown. We can see that these are two intersecting lines, so we know that the opposite angle is going to be equal. We also know that these lines here create right angles, and therefore this missing angle here between the normal force and the y component of the normal force is also going to then be equal to theta. We now can see that the x component of the normal force is going to be equal to n sine theta, and the y component of the normal force is going to be equal to n cosine theta. Now we want to break up the forces and the accelerations into the x and the y directions. So we know that when we're dealing with the x direction, we are dealing with the centripetal force, which in this case is the x component of the normal force, which we said was equal to n sine theta. And we also know that the centripetal acceleration is equal to v squared over r. So this is Newton's second law applied just towards in the x direction. Now let's look at the y direction. So in the y direction, we have the y component of the normal force and the weight force. And we also know that the car is not accelerating in the y direction. So we can set this equal to 0. And then when we solve, we see that n cosine of theta equals the mass times gravity. Now, just for an extra little relationship between a few variables, we can combine these two equations by dividing them by one another. And we see that the normal forces and the masses cancel. And we find that the tangent of theta equals v squared over the radius times gravity. So this relationship can be used in the future situations when you are just solving for one of these variables.